Hi everyone. Today's lecture is about confidence interval for proportions. So in the last lecture, we learned about sampling distribution, we learned about parameter and statistic, and sampling distribution. I told you that sampling distribution is different from sample distribution, and I told you that central limit theorem is very important. That was about the fact that the mean of a random sample is a random variable whose sampling distribution can be approximated by a normal model. And the larger the sample, the better the approximation will be. And this works no matter what the original data distribution is. And the sampling distribution of proportion can be modeled with a normal model with mean p and standard deviation of square root of pq divided by n. And the sampling distribution of a mean can be modeled with a normal model with a mean mu and standard deviation divided by square root of n. So let's revisit what we learned in the last lecture. We saw this is a population model that we cannot observe. We assume that we draw one real sample that is solid line of size n and show its histogram and summary statistic. And we keep going. Like imagine that us drawing many other samples with the same sample size, and also we gather all the mean values into one histogram. And this is the sampling distribution, and central limit theorem assure that the shape of this histogram is going to be a normal model. But as we talked about in the class, we cannot really know the mean and standard deviation of the sampling distribution because it's about the population parameter. Then what should we do? Let's use an example data about the Facebook use. So late in 2010, there was a survey. Pew Research surveyed the US residents about their use of social networking sites. And among 156 respondents who aged 18 to 22, 48 says that they update their status at least daily. The proportion of those who update their status daily was 48 among 156, that is 30.8%. We don't know about the population P, the population parameter. Then what can we say about the population P with P hat? So what we know about the sampling distribution. The sampling distribution model of P hat is going to be centered around P, population P. And the standard deviation of the sampling distribution is going to be population level parameter P times Q. Here Q is 1 minus P, as you remember, divided by n square root. So when we estimate the standard deviation of a sampling distribution, given that we don't know the population parameter P and Q, we have to use the sample standard deviation. The estimate of standard deviation, we call it a standard error. So for sample proportion P hat, the standard error is this, that is using the P hat and Q hat. It's different from PQ, right? So this is the standard deviation of sampling distribution, but we don't know the P and Q. Therefore, we are using P hat and Q hat, and we call it standard error. So for the Facebook users, standard error of the P hat is going to be calculated with this equation and 3.7%. What does that mean? Because SE is the estimated standard deviation of the sampling distribution, these two SE area under the curve under this normal distribution will be around 95%, as we learned about 68, 95, and 99.7 rule, right? Using this sampling distribution and standard error, we can calculate the confidence interval. To understand what the confidence interval is, we need to start from P hat's point of view. So from the P hat's point of view, 95% chance that P is no more than 2 standard errors away from me. Like, let's say there is a P hat, and then it assures that P is within the 2 standard error range. And I'm 95% sure that P will be within my 2 SE, standard error. This is what P hat is saying. And even if my interval catch P is saying that my interval, this 2 SE interval catch P, I still don't know its true value, but the best I can do is an interval. So P hat can do the interval and then assure that P, true P, the population P, is within that interval. And actually we can do bidirectional interval, and that really guarantee to capture P with 95% confidence. What can we really say about P for our example data. I'm going to tell you what we cannot say based on this confidence interval. 30.8% of all Facebook users between the ages of 18 and 22 update their status daily. No, we cannot say that because we have only sample, not the population. We cannot talk about all Facebook users. Also, this is the wrong statement. It is probably truly that 30.8% of all Facebook users between the ages of 18 and 22 update their status daily. No, we don't know the true population parameter P. So again, it's not about all Facebook users. So we are getting closer, but yeah, we don't know exactly what proportion of Facebook users between the ages of 18 and 22 update their status daily. That's true. But we know that it's within the interval 30.8% plus minus 2 times 3.7%. This is a SE, 2 SE. This is that. But do we really know that's within the interval? So we can change that into, we don't know exactly what the proportion of Facebook users between the ages of 18 and 22 update their status daily, but the interval from this and that probably contains the true proportion. That's correct, but we can say more than that. So this is a correct statement. We are 95% confident that between 23.4% and 38.2% of Facebook users between the ages of 18 and 22 update their status at least daily. So this is okay. So what does confidence interval really means? When we repeat the sampling over and over, 95% of sample confidence interval will include the true P. So there could be some cases, some samples that does not include the true P, but 95% of time it is gonna include the P. So we are confident that 95% confident that my samples confidence interval include the P. So that's what does confidence interval really means. So this is another cartoon. Each line is a sample. So you got this sample, you got this sample again. You are sampling or studying again and again. And then when you are repeating the experiment or the survey, 95% of times the interval will include the true P. So each sample proportion can be used to make confidence interval, as I showed you here. And the central limit theorem assures that in the long run, 95% of the intervals cover the true value, and only 5% are wrong. And the confidence intervals are random because they are based on the random samples, right? And our confidence or our uncertainty is about the interval, not the true proportion. And there's a trade-off between certainty versus precision. So as I said, our confidence interval has this form. So P hat. So this is an estimate plus minus some standard error. Here, 2 times standard error of the P hat is called the margin of error, ME. And any population parameter, proportion, mean, regression, slope, can be estimated with some margin of error. So the general form is actually estimate, that's from my data, plus minus margin of error. And margin of error can be 95% confidence interval, that's around 2 SE, and 99.7% confidence interval is going to be 3 times as standard error. For the 99.7% confidence, we can use 3 times standard error, and the interval gets broader, the larger. It covers more space. And we can go further. The more confident we want to be, the larger the margin of error must be. We can even make it into 100% confidence. We can say the proportion of Facebook users who update daily is between 0 and 100%. Is this useful? No. It doesn't mean anything, right? Or we can give a very narrow interval like 30.7% to 30.9% with very low confidence. So is this going to be useful as well? Maybe not. So we want to have a certain level of confidence and narrow margin of error. So there is a trade-off. If we want to be really sure, confident, the margin of error becomes big, And if we want small margin of error, my confidence becomes really low. So every confidence interval is a balance between certainty and precision. 90%, 95%, 99% are commonly used, and 95% is most commonly used. And there's a critical values. What is critical value? That is the number of standard errors. For example, we talked about 2 SE, 3 SE, and so on, and 2 and 3, these numbers are critical value and denoted as Z star. For 95% confidence interval, the precise critical value Z star is 1.96. Though we use 2 to make it simple, but it actually is 1.96. And for a 90% confidence interval, the critical value is 1.645. This is really Z value. When using confidence interval, there are assumptions, but it's really same with the assumptions and conditions that we talked about in the last lecture. So we can use this standard error when we want to choose our sample size. As we said, margin of error can be expressed like this: Z star, that is critical value, times standard error, that is P hat Q hat divided by N, and square root of that. If we want 3% margin of error for 95% confidence, because it's a proportion, the margin of error is also proportion. And Z star, for the 95% confidence, Z star, the critical value is 1.96. Given that this is a margin of error we want, and this is the critical value that we are going to use, and this is the standard error we can get from the sample. But if we don't know P hat, because it's going to be before we conduct any experiment, because we want to use this to choose our sample size, because it is likely that we don't know the P hat, so we can just take its maximum. P hat equals 0.5, and then P hat times Q hat becomes 0.25. That's the maximum value that we can get. And then from this equation, we can get root N should be around 32.67. N equals the square of 32.67, and it's around 1,000 people. So then our sample size should be 1,068, rounding up. And as you see here, as we have larger sample, the margin of error becomes smaller. Therefore, it really depends on margin of error we want to have, and then we can get the sample size. Okay, that's it for this lecture, and we learned about standard error and margin of error. So that's it for today. Don't forget to complete the quiz. See you in the class.